Hello everyone, welcome to my YouTube video. Today we are going to find what copy fail is. So first of all, I will I'll run the copy fails related command. So python 3. So if I run this and check who am I, it will become root. So we can have we can get the root shell. So we are going to understand why it works. At a high level, copy fail allows an unprivileged local user to write 4 control bytes at a time into the page cache of a readable file. So if we target a set UID root binary like user binsu, so user binsu, we can place each cached executable bytes with a tiny payload, execute it, and get a root shell. So this copy fail is Linux local privilege escalation, which can be shortened to LPE. So that means the attacker already has some form of local code execution. For example, a low privilege shell, so SSH access as a normal user, and something like this. So this copy fails means that attacker already has local code execution, then abuses this copy fail kernel bug and then become root. So in real world attack chains, the kind of LPE local privilege escalation bugs are extremely valuable because they turn a low privilege foothold into full system control. So copy fail lets an unprivileged user write 4 control bytes into the page cache of any readable file. So it's like 4 control bytes into the page cache and of any readable file in this code. So it should be user binsu. So Linux uses the page cache when reading and executing files. So if we corrupt the cached copy of user binsu, then for execution purposes, we may have effectively changed what the kernel loads, even though the file on disk remains unchanged. So what is page cache? So if we execute user binsu, there should be original binary in the disk, and in the RAM page cache there should be cached copy used by read method or something like this. And the page cache is a performance feature in the Linux kernel. Reading from disk is slow, which is original binary. Reading from RAM is fast, so Linux caches file contents in memory. When the process reads a file, Linux often does this: check whether the file data is already in the page cache. If yes, return it from memory. If no, read it from disk, place it in the page cache, then return it. This also matters for executable files. So when Linux executes a binary, the kernel loads file back pages into memory. Those pages are tied to the file's cached contents. So if an attacker can corrupt the page cache of an executable, they may influence what gets executed. So this copy fails is more like the exploit corrupts the cached in-memory copy of user binsu, not the original binary in disk file. So this matters for detection and forensics. So we are going to check why we are targeting this user binsu file. So this is the set UID root binary. If you look at the permission here, so the S means the set UID bit is set. Set UID means when this file is executed, run it with the privileges of the file owner, which should be the root. So when a normal user executes user binsu, the kernel grants the process elevated privileges because the file metadata says the owner is root and the setuid bit is enabled. So normally this is safe because users can execute user binsu, but they cannot modify it. But copy-fail breaks that assumption. The exploit does not need to modify the disk file, it corrupts the page cache, which resides in RAM of user binsu. So the kernel will see in the cached bytes there should be the attacker controlled payload. So we have root on setuid metadata in, and then attacker controlled cached executable byte, which should be our payload. It will lead to the root code execution. So we will exit this, and we will, if we check this file copy fails, and I think I can use less pager. So if we check this, we can find the something like this, socket.af ALG. So this is Linux socket interface to the kernel crypto API. So this is the socket family. This is not for networking. It is an interface that lets user space talk to the kernel crypto API. So with this socket family, in this code, in this code, so we can ask to perform this cryptographic operation for us. So in this copy pairs, this should be the related algorithm path, which goes to AEAD crypto interface. AEAD means authenticated encryption with associated data. So, but we are not interested in encryption security here. We care because this specific kernel crypto path mishandles memory. So what is authencesn, which is authentication, encryption, extended sequence number handling. It is a Linux kernel crypto template. So the bug is not that the kind of encryption is broken or weak. This bug is in how the kernel implementation handles memory buffers during the operation. Specifically, the copy-fail note describes the root issue as encryption extended sequence number using the color destination buffer as a scratch pad, writing 4 bytes beyond the legitimate output region, and failing to keep that right inside the intended destination buffer. That creates the 4-byte write primitive. So when we look into this, there should be also something like os.splice method, which is move data between file descriptors inside the kernel. Splice method is a Linux system call, so it can move data like file back to kernel page and pipe and then socket. The important phrase is file back to kernel page. With Splice, file data can move through kernel structures without the usual user space copy. In copy fail, this matters because Splice can handle page cached backed file pages into the crypto subsystem. So the exploit creates the data path like the user bins to page cache pages, and then splice, and then pipe and splice, and then the crypto subsystem AF ALG socket, Linux socket family, and then authentication, encryption, extended sequence number, vulnerable handling for memory. This is where magic happens. So crypto operations often need to process data that is not stored in one continuous block of memory. Instead, the data may be scattered across multiple memory locations. So the kernel uses structures called scatter gather list. So it should be like entry 1, memory page A, and the by like length of this, and entry 2, memory page B, and something like this. The crypto code can process this as one logical message even though the memory is physically split up. Copy fail happens because the kernel loses track of which pages are safe to write to. So the kernel thinks it is doing crypto scratch buffer work, but it ends up modifying cached file content. So if we check this, the process will be, there will be unprivileged user, and then there is AF ALG socket, and this authentication, encryption, extended sequence number method, and using send message with, I think the chunk size should be 4, and splice the readable file into a AF ALG socket family, and then scatter gather confusion and 4-byte write into page cache, and override cached set UID binary, and then write 4 bytes, and set UID binary, and 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 then we can get the root shell. So if I explain this again, so the attacker starts as a normal user, and they create an AF ALG socket and bind it to authentication, encryption, extended sequence number method. Then they send carefully shared AEAD metadata and controlled byte, and they use the splice to move data from a readable set UID binary such as user binsu into the crypto operation. Because of the bug, the crypto code writes 4 attacked control bytes into the page cache of the file. So do that once and you write 4 bytes. So there should be while until the payload. So we will do multiple times to write the 160 byte payload. and then execute user binsu. The kernel honors the setuid root metadata, but the cached bytes now start with attacker controlled ELF payload, and then we can get root shell. So copy pair is different from many other local privilege escalations. So and if we look into the copy pairs page, I believe maybe copy. So there should be also mitigation. So patch first, and before we can patch, disable the ALG AEAD module, which is we also have used. So if we summarize this, Linux caches file contents in RAM using the page cache, and then we will load executable bytes from the cache, and we will use the user binsu target, which is root owned and has setuid. So if we can corrupts cached byte, we can influence what runs as root. And AF ALG Linux socket family exposes kernel crypto to user space. Authentication encryption's extended sequence number has a logic bug in its buffer handling. Splice method can bit page cache backed file page into AF ALG. The bug creates a 4-byte controlled page cache write. So repeating the primitive writes a tiny ELF root shell payload, and executing the su runs the cached payload with root privileges. And then we are going to analyze this code from this at this stage. So we are going to open the user binsu read only and decompress a tiny x82 underscore 64 root shell ELF payload, and we will use AF ALG, which should be here, and authentication encryption sequence extended sequence number, and plus the splice method to write the payload into user binsu's binary page cache, and we will execute su. If this system is vulnerable, we can get a root shell. So if we check this, there should be also effective version. If your kernel was built in, and so like this. So the important primitive is in this code is write 4 control byte at a chosen offset inside the page cache of a readable file. So we will repeat the operation like write bytes 0 to 3, 4 to 7, 8 to 11. So as you can write 4 bytes at a time. So I will explain this from the scratch. So the OS module gives us low-level operating system functionality. So we can use the splice method, pipe method to create a Unix pipe, and then we can also open the target user bin su, and we can also execute su with this OS library, and using zlib we will decompress the decompress the payload later, and the socket module to create an AF ALG socket. So AF ALG is a Linux socket interface to the kernel crypto API. The crypto API path is where the vulnerability is triggered. And there is AF ALG constant. This so if we check this website, we can find the 279 is Sol ALG socket level values, something like this. And ALG set key, this one constant means sets the crypto key, and this is set the initialization vector. So if you check the CVC encryption like this, it uses like random initialization vector for the first block to ensure, so which looks to be used for the encryption. And the 3 is set the operation type, and 4 is set the AEAD associated data length, and 5 is set the AEAD authentication text size. So these are the AF ALG socket configuration constants. So our target will be user bin su, which is commonly root owned setuid binary. So, and chunk size will be 4 because copy fail writes 4 bytes at a time. That is why we write the payload in 4 byte chunks. So this hex to byte helper function will convert hex text into raw byte. So, and then we will going to check this write 4 byte method. So target fd will be which is related to our target with read-only mode, and target offset is offset where the 4 bytes should land, and payload chunk is the 4 bytes we want to write. So if we check this, payload function is 4 bytes, so which looks to be related to 4. So which means so if you like target fd, which is user bin su with read only mode, and if the target offset is 0 and payload chunk is 0:4, then write the first 4 page bytes at offset 0 inside the user bin su's page cache. First for payload. And then we can move to this part. So it uses AF ALG socket family, and sockets should be sequence packet. It means create a socket into the Linux kernel crypto API. So this matters because the vulnerability is reachable through the kernel crypto system. and then we can bind to vulnerable crypto algorithm. The first value AEAD means authenticated encryption with associated data, and second is authentication encryption extended sequence number is the exact crypto construction. So this is the kernel crypto template involved in this fork, and then it is authentication component and encryption component. So we are choosing this algorithm path because the vulnerable kernel logic is reachable here. And we can move to the next line. Encryption key length, and then so this is actual key material. So if we check this, it has like since we consider 2 hex character to 1 byte, so this should be 8 bytes and 32 bytes, so total 40 bytes. And this sets the crypto key, and this sets the AAD authentication text size. So since it has like chunk size, so we understand that the AAD authentication size will be 4, and ALG socket is the configured crypto interface, and this will be actual crypto request. The underscore means the ignoring the second returned value. So this line is subtle and important. So when we check this again, if we set this 0, and it should be like 0 to 4, then it should be 0 plus 4, and the splice length will be 4. So the target offset is where we want the 4 byte write to land. So if we want to write at offset 0, this value will be 0 plus 4, so 4. If we want to write at offset 4, it will be 4 plus 4, so the splice length will be 8. And this will create the null byte, literally. So we can check the operation socket send message. The send message can send normal data, ancillary control messages, and flags. So the normal data is this one, so payload chunk. So this should be 4, since the chunk size is, we define this as 4. So it will be like A, and the payload chunk will be so if the offset is 0, offset is 0, so it will be like from 0 byte to 3 bytes will be the A pillar, and then next 4 bytes will be controlled payload chunk. And the first one will set the operation type, and the second one is set the initialization vector, and third one will set the associated data length, AAD associated data length. So it will be like 08000000. I think I can. So this means that we can inform that more data is coming and do not finalize this crypto request yet. It will be more. So that matters because we still need to send file-backed data into the operation socket using splice method. And we will going to create the pipe, so it will be read file descriptor and write file descriptor. So pipe has two ends, it is read end and write end. Why do we need a pipe? Because splice commonly moves data like this: file, and then pipe, and then socket. In this exploit, the data path will be user bins su, file that we want, and then pipe, and then AF ALG operation socket. So the pipe will become the bridge. And if you check this, right, FD, so target FD will be like target user bin su file with read only, and but we will use this read only file descriptor to, and this is the right end of the pipe, and splice length will be offset +4, and the offset source is 0, which means starting reading from offset 0 of user bin su. So if target offset is 0, it will splice first 4 bytes of user bin su. If target offset is 4, then splice the first 4 bytes and more. And the second splice will pipe to AF ALG socket family. So it will move the data from the pipe into the AF ALG operation socket. So operation socket file no method returns the integer file descriptor for the socket. So it will be like user bin su page cached data, splice, pipe, and then splice, and then AF ALG operation socket. This is critical. The vulnerability depends on page cache backed file data entering the kernel crypto path. A normal read into Python bytes would not create the same situation. The splice preserves the kernel level data path needed for the bug. So this try except call triggers the kernel to process the queued crypto request. So the exploit does not care about return data. It cares about the side effect. So when the kernel processes the request, the vulnerable authentication encryption extended sequence number logic performs the 4-byte write into the target file's page cache. So why we said OS error? So for example, authentication may fail, but the exploit may still have achieved the memory corruption side effect. So the script ignores the error. So now we move to the main flow. So we will open this user binsu file as a read only. That means the script does not have normal write permission to the write file. This is the whole point of the kernel bug. Normally, read-only file descriptor should never allow modification, but through copy fail, so we will use this AF ALG authentication encryption extended sequence number bug. We can perform the page cache corruption. Then payload offset is 0 sets the starting offset for writing the payload. We start at 0 because we are replacing the beginning of the cached executable byte. So, and this payload command builds the payload. This is stored as compressed hex. So there should be hex string, which is converts to bytes and decompress, and we can get the mini I think tiny ELF executable. So we can validate this command. So I've also made the comment like here sudo byte I can just cat test py. So what will payload return like this? Then it will become, if we run this, it will become like this. And I can also check the size in case. Then it will be like print length of the payload so it will be 160 bytes. So it will be also 160 bytes the payload is. And if we check this, check the output again, it says like it will become the ELF. So ELF usually starts with this and ELF. So by writing a tiny ELF payload into the cached beginning of user binsu, the kernel loaded as an executable. So the loop writes the full payload into the page cache, so 160. So the chunk size will be 4. So each iteration writes 4 bytes. So if the payload is 160 like this, it will like run 40 times. And the first chunk is especially important. it writes the if you check this, it will be 7F. I think it is 4.5. It is 4C, 4.6 as a hex value. Like if you check like 7F, 4.5, 4C, 4, then it will be like ELF like this at offset 0. That is the ELF magic. After the loop finishes, the cached beginning of user binsu contains the mini ELF root shell payload. The disk file may be still be unchanged. The page cache is what has been corrupted. So finally, the script executes su. Normally, this would run user binsu, but at this moment, the page cache of user binsu has been corrupted. So the kernel sees the file metadata has like root owner and which has set UID, and then also sees the cached executable byte, which is attacker controlled ELF payload. So the kernel applies set UID root privileges, then loads the cached executable content. The payload runs as root and launches bin sh. This is how the script gets a root shell. So if we summarize this, we import OS zlib socket library and define the AF ALG constant, set target to user binsu, define helper function, and define the write for bytes method, and we open the user binsu as read only, and we decompress the mini ELF payload. We loop over payload in 4 byte chunks, and for each iteration, so we create the AF ALG socket, and we bind this with authentication encryption extended sequence number method, which should be vulnerable, like affected in this vulnerability, and set the 40 bytes and send AAAAN chunk as associated data. So payload chunk, this one. So if it's like, if the offset is 0, it should be 0 to 3 as an array. So it should be 0 to 3. So, and then splice the user binsu into pipe, and splice pipe into a AF ALG socket, and this will trigger the operation socket. Accept brain socket, and this will trigger kernel processing, and 4 bytes land in page cache, and then we will execute su, and payload runs with ZUID root privileges. So the core primitive should be controlled 4 byte page cache write. The privilege escalation comes from the target choice user binsu is ZUID root. So the binary result comes from combining override cache setuid binary plus execute, so then it will get root shell. So the primitive will be 4-byte control write, the object will be readable by page cache, and as target is setuid root binary like user binsu file, and we can get the root shell in the end. Thank you so much.